Hey everybody, welcome back to 113, this time again from the little remote version of 113. I was looking at a different number, 15. Just as a reminder, so obviously we're fully remote for this section today, and there is no afternoon section. So if you're in the 3 to 4 p.m. class, that won't happen. There's no remote version and there's no in-person version for that one either. Otherwise, the only other reminder that I can think of at the moment is that homework 4, I think, is due today. So make sure you get that uploaded to Canvas later today. By the way, none of the stuff that we've been doing today or Wednesday, anything with the solving systems of equations, is needed for the homework. The only function that you need to solve equations on your homework is F0. You shouldn't be using Fsolve anywhere on your homework yet. That's what the next homework is going to be about. In fact, I think there's a little set of instructions at the top of your homework that says just use F0. Don't use any other functions. So that out of the way, we're going to keep talking about solving systems of equations. And we're just going to solve one system of equations today, but we're going to do it in 2 ways, because if we see it over in Excel, we can learn a few more things about the way that the algorithm is working and why it's sort of so much more challenging to solve systems of equations than it is to find solutions to just a single equation. But also we're going to use some of the ideas that we've got here to talk about some of the problems with solving systems of equations, probably on Monday, maybe Wednesday. It depends on when we get there. So there are some tricks you have to do when you are solving certain systems of equations that are a little bit easier to see if we have the time to write them out in Excel. So let's go ahead and switch over there. So this is where we left off. Well, it's more than what we had left off on. This is where we had actually started on Wednesday's lecture. We're generally going to be solving a system of n equations for n unknowns. Most of the time in here it'll be like 2 or 3 or maybe 4 equations. It scales okay to larger systems, but I can't think of too many times where we have to solve 8 or 9 or 10 systems of nonlinear equations. We may have to solve that many linear equations, but we use linear algebra for that rather than something like the Fsolve. And that's a topic for Math 18, your linear algebra course. We're not really going to get into that here. So the general idea is we start with 2 equations, so I've just labeled them 1 and 2 right here. We rearrange those equations to root finding form, which is the same as what we had done for a single equation, but now we bundle them as a column vector. So we think of the first row as the first equation and the second row as the second equation. Our target sort of variable is similar to the target that we had before, which is to say that when that target variable, when all elements of that are equal to 0, then we say we have found a solution. It is typically not the only solution, and that is something that we'll talk about more today, and is one of the things that's really challenging with systems of nonlinear equations, is it's hard to find out when you've found quote-unquote the solution, because there's usually more than one. And we don't typically have the ability to plot these functions in a convenient way to look for more roots in the way that we did with a single function. So whenever possible, we try to use a single function because the tools that we have for that are much more powerful. Once we have this idea of arranging them into column vectors, we define some variables that we're going to use over and over and over again, regardless of how big the system is. So we think of our unknowns, in this case x and y, as being bundled into a column vector, and we call that column vector y. We think of our solution as coming as x and y sol in a column vector. We call that y sol. And similarly, our guess for the initial solution, we think of that as a column vector containing a guess for x and then a guess for y, and we call that y guess. The syntax for Fsolve looks very similar to the syntax for F0, and that's on purpose. I'm trying to keep it looking fairly similar to what we had for F0. The difference is that we use that capital Y as our column vector for all of these values. Otherwise, we change the word F0 to Fsolve, and we keep the syntax the same as it was for F0. It is subject to these two limitations that we've got here, which is you can't bracket the roots like you did for F0. So you have to provide initial guesses. You can't provide sort of a column vector of brackets. That won't work. And it can also be really hard to get that initial guess, and that's part of what we're going to bump into here. So we're going to start here with our example problem. We're going to solve it once in Excel to get a little bit of an idea of A, how hard it is, but B, also what the computer is doing, because it really is just an iterative process. And B, like I said earlier, we've got some tools that we can use in here that'll help us better understand some limiting cases, or I should say some edge cases where Fsolve can have a hard time solving stuff. There's a way to identify those and correct them, at least in some common situations. So I'm going to start with adding a new sheet over here, and we'll just call this our example for today. So our example, I'm at 140. We can probably do this. We can minimize this ribbon for now too. So we're going to solve the system of equations that consists of, as I said, in this case, just two equations. So the first one is going to be that y is equal to the square root of x, and the second one is going to be that 4 is equal to x plus y. So this will be equation 1, and this will be equation 2. Certainly, you could imagine this would be a candidate for substituting one of those equations into the other one and then just solving for that variable. So for example, you could take equation 2 and just substitute it into equation 3, and now you've got one equation with one unknown, and you could put that into F0 and solve it that way. That is certainly possible, and that's actually the preferred route if you can swing it mathematically. We're going to assume that that's not possible. That is not always possible. And so we're just going to leave these separated and solve them both simultaneously, and sort of ignore for the moment the fact that we could have separated or combined those into one equation and solved them that way. So what do? Well, the first thing that we do is we think of what the variables are. That capital Y is going to consist of the variables x and lowercase y. We don't actually need to use those anywhere in here, but I'm going to write them out anyway just so that we remember that that's what they are. So they're going to be x and y. That's going to be what our y is. We also have a y guess, which is again going to be a column vector. And so we need a guess for y and a guess for x. So the pattern of this is that x guess is the first one and y guess is the second one, or whatever your variables are. I'm just going to guess, if I look at the first equation, it looks like 0 satisfies that equation. So I'm going to say 0 for x guess. The result of that would also be that y would have to be 0. So I'm just going to pick 0, 0 as my initial guess. This is one of those cases where it's a kind of a pure math problem. We don't know any physical significance of x or y, but often these values, these guesses will come from something that's noted in the problem. Maybe it's a mass flow rate or a volume or a temperature or pressure or something like that, and we'll get an idea of what a reasonable value for that would be. The next thing we're going to do is that target matrix, or target, I should say, vector. The target is going to be a column vector of our two equations. So the first one is going to be our equation 1, but it's going to be equation 1 in root finding form. So we're going to rearrange this to say square root of x minus y. And similarly, our second one is going to be equation 2 in root finding form. So this is going to be x plus y minus 4. So now it does somewhat become a question of what is our x and our y? Well, the way that Matlab is going to think about this is if I move this down a little bit, it's going to base its calculation on the solution value, which is y-sol. So this is going to consist of x-sol and y-sol. But you can see here an illustration of why we need an initial guess. The initial guess is what it initially puts into x-sol and y-sol so that it can get started with its target operation, so that it can say, all right, I got to get this close to 0. Where do I start? Well, I can't generate, excuse me, I can't generate my first estimate of a target until you tell me roughly where to go with my solutions. So the first values for xsol and ysol come from yguess. We don't have to do that. That's what happens within the fsolve function when it's operating. We just have to tell it what the xguess and the yguess are. So all that really happens here is these values get copied down, right? I have 2 zeros here. Those become my first values that are in here. Now I'm in a position where I can evaluate my target given this as my proposed solution. So I can come down here and say, okay, take the square root of my x value and subtract from it y. So I'm going to calculate my target value as the square root of x minus y for equation 1. If I've got a good solution, this value is going to come out close to 0 or exactly 0. We picked our yguess so that that one happens to be exactly 0. But if we go ahead and evaluate the second one, which is x plus y minus 4, we'll see that one doesn't work so well, right? That one is down to negative 4. So when you see this equation 1 in root finding form and equation 2 in root finding form, what it's doing is evaluating those equations at the proposed solution value. How do you get started with the solution value? You take a guess, right? That's where our guess comes in. At this point, we have, if we're thinking in Matlab terms, we have coded everything that we would need inside of Matlab to say, okay, Fsolve, go ahead and have your best effort at solving this system. Do it until these two values are close to 0. But if you just try changing your guess a little bit, it's kind of hard, right? So 0, 0 gives me 0 and negative 4. Let's say that I change this to like 1 and 1. Okay, that seems to have helped a little bit, right? Because now it's 0 and 2. But where do I really go for my next guess? Maybe I up them both and go to 2 and 2. Okay, a little bit better. This one went negative. How do I keep going, right? It's tricky. If I go to 3 and 3, that doesn't really help. I got a little bit too far away. So somehow in between that phase space of 2 and 2 and 3 and 3, it seems like there could be a solution or something that gets close to a solution. So 2 and 2 is not bad. You know, you can play around with maybe it's 3 and 2 or something like that. But 3 and 2 made the second equation worse. So, okay, 2 and 2 is better. Maybe it's 2 and 3. Did that really help or not? It's very hard to tell whether or not your guesses are helping, and more importantly, which direction your next guess should go. And that's what the algorithm of Fsolve will do for us. What I want to illustrate here is if I did need to solve this inside of Excel, there is a way that I can do it. The requirement for Excel to solve a system of equations is two things. Okay, to solve this in Excel, the first thing you're going to do is use, which may require you to install, the solver package, the solver tool. The solver tool comes with Excel, so it's not like you have to go download anything. For whatever reason, they don't include it as sort of default in your ribbon, but the easiest way to find this, if we say 1A, is search for add-ins in your search bar. So the search bar that I'm referring to is this bar up here at the top, which I can kind of hover my mouse on enough to highlight. So you can look for add-ins up here, and you just search for add-ins. And then within the add-ins window, select Solver. If you're on the online version of Excel, I don't know if it works the same. But if you're on one of the installed versions of Excel that you've installed on your computer, you should have a search bar that looks something like that. Maybe it's moved somewhere else. And so I'm going to search for add-ins. You want the one, not insert an add-in like this, but you want the one that looks like a gear. So you want to be able to manage the add-ins that are available. So you should have something that looks like that. If you don't have it, it's okay. It's not going to be critical for the rest of our lecture today. So if you can't find it, just hang out for a few minutes and we'll be done with this momentarily. So I'm going to click add-ins. You should have a number of different add-ins depending on what you selected when you installed Excel in the first place. But regardless of what you had installed, there should be one that's called the Solver add-in. And you can see its description is it's a tool for optimization and equation solving. That's exactly what we want. So select that. Honestly, that analysis tool pack's not a bad one too. If you don't have that already installed, it's just useful for other stuff, but you can see it's good for statistics and engineering analysis. So you might want that just for your own purposes. But Solver add-in is really the one that we want. So I'm going to click OK. We'll just wait a moment for it to install. And then the last part is now that supposedly Solver has been added as an add-in, you want to go to Data, and then on the right, there's Solver. I should say Data on your ribbon. Data ribbon. And over on the right should be Solver. So Data, way over here on the right, is Solver. Before we go into Solver, we do need to complete one more step in Excel. The Solver thing, you should only need to do that once. Like if you just did it now and you don't change computers, it should always be there, right? The next time you open Excel, you shouldn't have to go reinstall Solver. So more commonly, we skip immediately to step 2, which is to define a target cell, or I should say define an objective cell, which I'll put in all caps just so that it's kind of noticeable. And we define this as the sum of squares of all target cells. The reason we have to do this is because the syntax for Solver, the interface for Solver, is going to say, I'm going to guess some variables over here. How will I know when I've got a correct guess? When this single cell over here is equal to 0. So somehow we have to combine all of these target cells, which we have as 2, into a single cell that says when that single cell is equal to 0, we have solved the equation. There are different ways that you can do that. One that you might think of is to just add the 2, because if they are both equal to 0, then their sum is also equal to 0. The downside with just plain old adding them is that one could be like minus 10 and one could be plus 10, and then their sum is 0, but you haven't really solved the system of equations, right? They're still very much not satisfied, and yet somehow they sum to 0. Hence why we tend to sum the squares of the target values. So we say equal this value squared plus this value squared. That gets rid of the problem of negative results in there. It just squares them. You could do like absolutes or something like that, and that would also be okay. So this is going to be our objective cell. And it's only for using Solver. This is not needed in Matlab. But we are going to come back to this idea because it helps us sort of visualize things on probably Monday or Wednesday's class. It is a common way that we can solve systems of equations is to create something that looks like an objective cell that somehow encapsulates a single answer to the question, have we solved the system of equations or not? So that's going to be our objective cell. Now we can run Solver. And the way that, before we get into Solver, the way that it's going to work is it's going to say, which values do you want me to solve for, which is going to be this one, the 0.345, right? I want to set that equal to a particular value. And which values am I allowed to vary? So in this case, it's going to be xsol and ysol. I'm allowed to pick those to be whatever I want them to be. So if we go into the data ribbon and go over to Solver, you should get a window that looks something like this. I'll scooch it over to the side so you can see it around my camera. And it sort of reads in a similar way to goal-seek when we were looking at solving one equation for one unknown. The first thing it asks you is, what's your objective cell? So set objective. In this case, it's going to be, for us, cell B16 in the way that I've done it here. To value of what? Well, it can maximize it, it can minimize it, or you can pick a specific value. We want to pick a specific value of 0, although minimizing would actually work here too, since we're dealing with the sum of squares, but we want to try to set it equal to a value of 0 if it can get there. And then by changing variable cells, and that's the part where you say, what are the things that Excel is allowed to change? So we're going to select our 2 solution variables here, which are again organized as a column vector. And there's one other thing which is defaulted to be checked, which is make the unconstrained variables non-negative. What that means is if you do nothing but just select the variables, Solver's only going to look for answers where those variables are positive. That is usually not what we want. It's often okay for those values to be negative. So for example, here, this is kind of a pure math problem. It's generally okay for those variables to be negative. There are all kinds of ways that you can add different conditions and say you're only allowed to look in certain places for this solution, which is kind of nice if you know where the solution is. In Solver, you can actually bracket your root and say it has to be between here and here, which is something that you can't do with Fsolve over in Matlab. So it is a pretty powerful little solver package. All we're going to do right now is just uncheck this and say search everywhere. Don't restrict anything. Don't say that anything has to be positive or negative. We're just going to see what happens if we say start searching. See what you can do. So I've unchecked that. Leave the solving algorithm as GRG nonlinear. It's fine. And then click solve. So I didn't find a solution. It says solver found a solution. All constraints and optimality are conditions are satisfied. That's the kind of message that you're looking for. You just wanted to say, I found an answer. If it says anything other than I found an answer, it probably didn't find a very good answer, and it's trying to tell you about that. And we're going to have to learn to interpret Fsolve over in Matlab in a similar way to say, if it says anything other than I found a solution, it probably didn't find a solution, not a very good one anyway. So we're going to just click OK here. We're not going to look at any of the reports that it can generate, and we're just going to look at what happened. It varied xsol and ysol within our capital Ysol vector until it found that this value was really close to 0. 7 times 10 to the 9th is fairly close to 0, but you can see that that is actually sort of a better estimate than the actual root finding expressions, because they're only like 10 to the minus 5 or something like that, but they're still pretty close to 0. The first one is 10 to the minus 5, and the second one is on the order of 10 to the minus 5, maybe 10 to the minus 4, if you wanted to round up a little bit. So it definitely found what I would consider to be a pretty fair solution of this. It did, however, depend on the initial guess. And so if we were to put our actual initial guess in there as 0 and 0 and run that solver again, everything is the same, right? We're doing the same objective function, changing the same set of cells, but our initial guess is different. If I go to solve this again, it did, in fact, find another solution there. That's great. Let's see what happens if we were to pick a different guess, right? Maybe we wanted to say 1, right? Right away we know that that's not going to work because we have a negative number in one of our target values. But how would we know that without actually seeing what the target values are? That's where Excel is nice, because Excel is saying you can't go negative on that first one because it is trying to create essentially the square root of a negative number. That kind of thing is harder to see in Matlab without using something like the debugger. And it's a little bit more frustrating because it's not always so obvious as I have a negative number and I took the square root of a negative number. That could be kind of hard for it to see. And so we have to use the debugger, interpret the output from Fsolve a little bit better or a little bit more carefully to get an idea of what could be the potential problem. But you can see now if we keep running the solver a few more times, it will generally keep converging back to the same solution. But once we knew that it couldn't be negative, we could constrain the variables to be non-negative, and it would find them just fine in those cases. But that indicates the importance of a good first guess, right? If my first guess were -1 and -1, or -4 in this case, Excel will tell me right away that that's a problem because I can see that there's a number error that sits here. And I could kind of track down the problem with that is it's a negative. But in Matlab, it's going to be a little bit harder to figure out, oh, the problem was specifically that Xsol was initially guessed as a negative number, and it produced a square root of a negative number on here, which is one of the nice things about Excel. We can see that right away. And in fact, it's not a bad idea to just kind of scooch our guess, bump our guess a little bit away from 0, 0, and make it a little bit further away so that the algorithm doesn't look in the negative direction. So that's how we solve it in Excel. I'm just going to wait a couple of moments here, and then we're going to switch over to Matlab and see how we can do the same thing over in Matlab. And then we might actually wrap it up a little bit early for our Friday. We might be done 5 or 10 minutes early. So I am over on Canvas chat too, but we'll just wait here for a couple of moments in case anybody's got any questions. But Matlab is next, so if you want to fire that up. Okay, no questions so far, so let's go ahead and switch over to Matlab. So we're going to solve most of these in scripts. So we're going to give ourselves a new script. I'll just delete whatever that old one was, and we'll call this one example 1. Let me zoom in a little bit just so that you can see my fonts a little bit better. We'll go up to, I think 12 should be okay. Yeah, that seems like it's okay. Now, what the heck? We'll go even a little bit bigger. I know it can be hard to see this stuff on phones, so nothing wrong with a size 14 font. So the general approach here looks very similar to what we found with root finding. So we write them, first we identify the equations and the unknowns. That can be challenging in and of itself, as you may have bumped into on homework 4 with problem 5, where you're doing the stair-stepping thing. Sometimes it can be hard to write out what those equations are and what the unknowns are. So that's a good first place. Here, for our example, it's just x and y. So that's the stuff that we're going to be solving. The next couple of steps, obviously rearranged a root finding form. We just did that. And then we need to write a local function for our root finding function. That still holds on this particular example. I'm going to give you some general advice on how to set that root finding function up. So advice for setting up root finding function. My first piece of advice is start with the definition that's standard. So start with a standard function definition. And I say standard specifically for root finding. So what that's going to end up looking like is something like function is equal to, you can call it target or output or something like that. I'll just call it out because that's what I usually call it, is equal to my root finding function as a function of y. And my advice here is always use y as your root finding function variable. The next step, and of course this would be accompanied by an end statement down here. Actually, you know what? Let's make this a live script because then we can actually put some example code inside of here. So advice for setting up Fsolve problems. So the first step, which I had said back here, start with the standard function definition for root finding. And now in Live Editor, there's actually a way to add example code without executing it. If you go over to the Insert tab, there's a code example on here. I've actually never clicked on this. And you can insert this, and it'll give you a window that gets formatted like code, but it's not actually code. It just looks like code. And so this is nice because it'll set this up. So we'll say output RFF of y, and then with an end function afterwards. So that's kind of where we get started. The next step after that is extract the variables from y. And I usually do this in the first few lines of the function. First few lines of function. So if we insert another code example here and just copy paste our previous one, what does that mean? Well, what that means is the first couple of lines, you can go in here and extract the variables that are sitting inside of y. So in our case, x is going to be from y of 1, and y is going to be from y of 2. Right? Remember that when we wrote this out, we had originally defined it as x and y, as being capital Y. So right away, we extract those values. Those variables. The advantage of doing something like that is it's typically a lot easier to write the remaining functions without having to remember that x is the first value of capital Y and y is the second value of capital Y. Now we can actually write those functions. That is the third step. Give yourself some space. Then write the target functions in root finding value, or root finding form, as columns in your out variable. So let's take a look at what that would look like. We'll insert a code example here. Give yourself some space. Here's some space. And now write them as the keyword here is columns in your out variable. So we have two equations that we have to solve. The first one will go in the first row, the second one will go in the second row. Remember, with indexing, if we were to just say out of 1 is equal to something and out of 2 is equal to something, this would actually specify a row vector, not a column vector. It will put the next one side by side with the first one. So we do need to specify which shape we're using. There's two different ways to do that. Typically, I will say just with a comma and say comma 1 for all of these. That'll ensure that you've always got a column vector. Another way that we could have done this is to actually pre-allocate out as a series of zeros with a number of rows equal to whatever we need and a number of columns equal to 1. You could do that too and then not have to worry about the extra indexing when you go to out. Either one is fine, whatever one seems most obvious to you. The way that you're going to see me generally write it is probably with the comma 1 after each one of these to ensure that I am defining a column vector. So here I can write those functions in root finding form. So with ours, those would look something like the square root of x minus y, and then 4 minus x minus y. This, you can see again the advantage of extracting the x and extracting the y from the columns or from the rows of capital Y. These expressions look human readable. So these look more human readable than an equivalent, which would also be correct. We could have also said square root of y of 1 minus y of 2. That would have been fine. That means the same thing. The equivalent version of this would have been something like 4 minus y of 1 minus y of 2. The problem with both of those is not that Matlab doesn't understand how to interpret them or that it would interpret them incorrectly. It's that if I come back and debug this, every time I look at y of 1, I have to make a mental substitution and say, did I actually get x here? Is that supposed to be x or is that supposed to be y? And did I get the right value? Here I've sort of offloaded that process up at the top of my script and said, if I can just guarantee I do it once up here, now I can just think about x instead of the indexing process. And so now when I come down here, I can make this look like the equation that I'm trying to solve, and therefore it's easier for me to debug it. But it's not strictly necessary to extract those values, but I would strongly recommend that you do it because with more complicated problems, it becomes so much easier, just incredibly easier to debug these equations when they're in a more human readable format. Once you've got this, this is your local function. But oftentimes the equations that you've got down here in root finding form require some intermediate calculations, right? All I do is I start with x and y, and given nothing but x and y, I have to be able to calculate everything that's down here. That happens to be the case here, but it is usually not the case. Usually, you'll need to fill in some more expressions and constants. Fill in the rest of your script, your function, with more constants, equations, variables, etc. So that's where this sort of some space that we gave ourselves previously might be things like defining constants. It might be calculating new values, something like that. It could be, I don't know, making decisions, right? You may need switch cases or something like that. So you might need switch cases or if statements, things like that. So for example, let's say that we're going to needlessly complicate our example here. Let's say that this value of 4 wasn't 4, but it was C0. So at the beginning of my function, all the function knows is what the value of x and y are. By the time it gets down here, it needs to know not only x and y, but also C0. And so you might end up having something like C0 is equal to 4. That would be fine, right? But it needs to be defined before you get down to the bottom so that the function knows that it's there. Or it could be more complicated, right? It could be something like a is equal to, I don't know, exponential of -4 plus the log of 3, all kinds of stuff like that. And then maybe b is some function of a. Maybe it's, let's see, the sine of a, something like that. And then maybe C0 is equal to, I'm just going to say b times 0 plus 4. Right? You can throw in all of those intermediate calculations in order to generate these expressions down here. In this case, I'm just filling in values so that they look like something. But all of that has to go in between there. And that's sort of what I mean by a sandwich approach, is you start off with a system that looks like this, right? You've got where you need to be at the end, and you've got where you're starting out at the beginning. Now you need to kind of fill in that sandwich until the two meet. Define everything else that you need in order to calculate the stuff at the bottom, starting from those values up at the top. Here we've just made it a little bit more complicated than it needs to be. So I'm going to save this since I haven't saved it yet. Save this as example 1. And then last but not least is set up and solve the script, the problem in the script with Fsolve. So now we're actually going to go ahead and solve this. So here I do actually need to write that function. So it'll look something like out is equal to RFF of y. I'm going to sandwich everything. So I'm going to start with x is equal to y of 1 and y is equal to y of 2. And then define, I'll give myself some space, although we don't need it in this particular problem, and say out of 1, 1. That's my first equation in root finding form, so square root of x minus y. That's equation 1 in root finding form. And out of 2, 1 is equal to 4 minus x minus y. This is equation 2 in root finding form. We don't actually need anything else. That's sufficient for this particular example. So the other stuff that we needed in there, we're just not going to fill it in. But in order to use Fsolve, we can set that up as our standard definition, which I'm not sure if did I include it up here? Standard function root definition for root finding. There is a standard definition for, or I shouldn't say standard definition, a standard template that you can use whenever you want to solve these, which is that ySolve is going to be equal to Fsolve at y of my root finding function of y and yGuess. You can use this pretty much every time. It's always going to look like that, right? Because it's always going to be a column vector that got bundled together, or that has bundled together a bunch of different variables. But we always call them y, and so we often can just use this standard template for a call to Fsolve. If you need to add additional parameters, you can do those in the same way that we had previously. So leave it at y, because that tells it what it's supposed to vary, and then you can add additional parameters this way. But most of the time it's just going to look like this. And so the only other thing that we need to do is define yGuess, which we're going to say is about 1 and 1. Remember, this has to be a column vector, hence the use of semicolon. It will often solve it okay if you give it a row vector, but every once in a while you get into a problem with mixing up row vectors and column vectors. You can then extract the values of xsol and ysol. This is going to be ysol of 1, and ysol is going to be capital Ysol of 2. And then if you wanted to type out the answers or display the answers somehow, you could use an fprintf and say something like, let's maybe tab over. Actually, we'll give a new line and then a tab, and say something like xsol and ysol are equal to percentage, say, 0.4f and percentage 0.4f. And then start a new line and say the first one's xsol and the second one's ysol. Just as an example of how you can do something with the solutions once you've got them. So that should solve our problem. Let's see if I made any typos. I'll run this. So notice what it says. Let me move my command window a little bit. In exactly the same way that Solver over in Excel popped up a window and said, here's the result of my effort, Fsolve will also tell you the results of its effort. This is what you want. You want it to say equation solved. If it says anything other than equation solved, look really hard, because you may have screwed it up a little bit. Like your initial guess might not be particularly good. You need that thing to say equation solved. If it doesn't say that, something's funky. You've probably made a typo. You haven't made a very good initial guess. And so you'll have to go back and refine those a little bit more. Once that happens, then you can go down here and look at, okay, well, what actually happened? It looks like xsol, ysol is 2.4384 and 1.5616, which if you compare that over to what we found in Excel, you'll see it's the same thing. Those came out, as far as we can tell, to be the same thing. Let's see if we can break it by changing our initial guess to a -1, and we'll see what that says. Excel or Matlab seemed to have solved it just fine. It can actually take square roots of negative numbers. Matlab is programmed in such a way that it's smart enough to know how to handle that, and it still was able to find us a real solution, right? Not an imaginary solution. So all of that is good. We can try bigger numbers and see if we can get something to break, but Solver's pretty solid for a lot of cases, so we could have a hard time getting this thing to break too much. Even here, it seems to be pretty good. Let's see if I can get one value to come up. If we just put the answer back in, sometimes we can get at least a different message. Nope, not really. It's solving this one just fine. This is great, right? This is what you want to see when you're solving a problem, is that I can throw in all kinds of different guesses here. I can even go back to my original 0, guess, and whatever value I'm throwing in as my initial guess, I'm getting the same answer each time. This is a concept called stability, which we're not really going to go into too much, but it's a good thing. Putting in different guesses and getting the same answer means that you've found a stable solution. It seems to really be 2.4384 and 1.5616. So I will wrap it up here. It's 12:45. There's no need to try and squeeze in one more topic in the last 5 minutes on a Friday afternoon. We will pick it up here on Monday's lecture. We'll do a couple more examples, and we'll look a little bit more about this concept of stability, as well as things that we can do to improve stability by what's called scaling. Sometimes our equations aren't giving us the same order of magnitude response for the same initial guess, and there are ways we can track that down. And so we will also look at that back here on Monday. So I will wrap it up here. Have a great weekend. Stay safe out there. And I will see you on Monday. Have a good one, everybody.